All right, thank you everyone. I know this is late, so I will hopefully add some value to the conversations that have already been really stellar today. So thank you again for the panelists. My name is Abhishek. I'm the product lead for foundational research at Google DeepMind. So my job is to translate a lot of the research from DeepMind into products. And today I want to explore what I think might be some of the root node problems in AI. Before that, I'll just kind of share DeepMind's mission is to build AI responsibly to benefit humanity. So we take every aspect of this very seriously. We're in the business of building AI. We want to focus on making it really responsible, and healthcare is an area where doing this with great care and caution and with the community is really important. And the way we do this is by what we call identifying root node problems. And I think when we look at a new problem space, we want to identify areas where we can focus on, such that if we could find a solution, we don't know if we can, but if we could find a solution there, it would have a cascading impact on the whole field, and lots of different solutions can emerge from those specific solutions. So I'll give you a few examples which are different from healthcare, so just bear with me for 7 or 8 slides where I will not talk about healthcare, and then I will come back to how that connects back into healthcare. So one of the early examples that we were dealing with, we picked on this problem called Go. And so Go is a game. It is a pretty complex game. The number of moves possible in this game are 10 to the power of 170. So this is 1 followed by 170 zeros possibilities for how this game could go. And it largely relies on intuition. So there's no calculation, and sometimes Go players will tell you that they just felt that this was the right move. And because there's no right set of rules on how you would win, this makes it impossible to write a good evaluation function. That am I playing a good move or a not so good move is a very hard problem. So I'll just bookmark this point, that this evaluation function that tells you whether you're getting a high reward or a low reward is a really important part of how we go about doing this. So the way we went about addressing this was we decided to mimic what these experts do. And instead of trying to create one, we wanted to learn an evaluation function. So we created this thing called AlphaGo, where it learned to play Go by playing against itself millions of times. So because we know the rules, basic rules of the games, we can write a simulator. The simulator can play against itself and generate a lot of trajectories of how the game went and understand whether the game ended up going well or not. You backtrack that and understand whether this, at any given state, whether you were taking the right decisions, and that gives you the evaluation function. And then to test AlphaGo's skills, we booked a challenge match with an 18-time world champion, Lee Sedol, and AlphaGo won the match 4-1. That was great, but there was an even bigger consequence. During the match, there was this game 2 where AlphaGo played this now famous move 37, which I think it put this tone on this 5th line, which everybody felt was a terrible idea, and nobody who's played Go before felt that this would lead to a winning strategy. But then 100 moves later, it connected perfectly with what AlphaGo ended up doing to eventually win the match. So after the match, Lee Sedol said about move 37 that I thought AlphaGo was based on probability calculations, and then it was merely a machine. But when I saw this move, I changed my mind. Surely AlphaGo is creative. So I think when you do this, when you can run these large sets of trajectories and learn the evaluation functions and then self-improve based on this, new things happen that you were not expecting earlier. So I'll just park this thought for a minute. The second area, and Chandu spoke briefly about this as well, I want to talk about. So we've been looking pretty closely at nuclear fusion for all the applied reasons, but also it's a fascinating technical problem. This is not a solved problem by any means, nowhere as close to how we've gotten with AlphaGo. But AI is helping make significant strides. And I bring up fusion because, like healthcare, the cost of experimentation here is very high. So getting things right does matter. And also, like healthcare, you're dealing with really complex physical systems. So the ability to run experiments at large scale to get all the data that you want is pretty limited. So in fusion, the root node problem is often stated as the plasma control problem, that this plasma behaves in lots of different ways. And there's just a lot of different states. Like just from a physics perspective, the system can end up in a lot of different states, and controlling the plasma in a few states that are actually ideal to generate the conditions under which fusion can happen is a very hard problem. So the challenge is that because this state space is so large, you can't experiment in the wild. But the way we could do this is by really simulating. So take all the physics knowledge, the actual work that physicists have done over the centuries, take all of that to really simulate as perfectly as possible, and you bring AI to bear on that problem to really accelerate the simulations and run a lot of trajectories, some of which will be nonsensical, some will really work, but you understand where the state of the system can go at different points in time. So the second point I want to bookmark is this importance of building a good simulator for these really complex systems, especially when the state space is really, really large. So again, you can start drawing parallels in your head to healthcare. I think the human body, given its complexity, has lots of different states in which it can end up going, and understanding how you can simulate this well is really important.